In episode 68, titled Bonding, When to Bundle Links and What Can Go Wrong, the focus is on bonding as the act of combining multiple physical links into one logical connection at the server or switch level. Bonding is attractive because it promises more throughput and better resilience with what looks like a simple configuration change. The exam tests bonding because it sits at the intersection of Layer 2 behavior, link aggregation expectations, and application traffic patterns, and it is easy to oversimplify. When bonding is done correctly, it can make maintenance safer and reduce outage risk when one link fails. When bonding is done incorrectly, it can create loops, intermittent drops, and performance surprises that are difficult to troubleshoot. The most important lesson is that bonding is a contract between both ends of the link, and the contract must match on both sides. This episode builds a clear understanding of bonding goals, common modes, misconfiguration risks, and the operational practices that keep bonded links stable. Before we continue, a quick note. This audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Bonding exists to pursue three related goals: throughput, redundancy, and failure tolerance. Throughput refers to increasing the total available capacity between systems by allowing traffic to use multiple physical links as a pool. Redundancy refers to maintaining connectivity when one member link fails, so the logical connection remains up on surviving members. Failure tolerance refers to the system's ability to absorb link interruptions without taking down applications, especially when links flap or when maintenance requires unplugging or replacing cables. These goals are often aligned but not identical, because a bond that provides redundancy does not always provide linear throughput gains for every traffic pattern. The exam expects you to reason about which goal is primary in a scenario, because the correct bonding mode depends on whether you are optimizing for continuous connectivity, for aggregate capacity, or for both. Bonding also supports operational flexibility because it allows you to change one member link at a time while the connection remains active. When you define the goal clearly, bonding becomes a deliberate design choice rather than a default tweak. The goal drives mode selection, testing priorities, and how you interpret performance results. Bonding modes can be understood conceptually as active backup versus load balance approaches, and this distinction is central to how bonding behaves during both normal operation and failure. Active backup means one link carries traffic while the other is idle or standby, and if the active link fails, the standby takes over. This mode prioritizes redundancy and simplicity because traffic uses only one path at a time, reducing the chance of out-of-order delivery and reducing the need for advanced switch support. Load balance modes distribute traffic across multiple links, allowing the bond to use more aggregate capacity and potentially improving performance for multi-flow workloads. Load balance modes still provide redundancy because if one member fails, traffic can be redistributed across remaining members, but they require more coordination and correct configuration to avoid misforwarding. The exam often tests whether you understand that active backup is about failover rather than about bandwidth pooling, while load balance is about pooling with more complexity. The mode choice affects not only throughput, but also the risk of misconfiguration and the types of failures you can expect. When you can explain these modes at a conceptual level, you can reason through scenario questions without relying on vendor terms. Matching the mode to switch support and application traffic behavior is the key directive, because a bond's effectiveness depends on what the switch can do and on how the application generates traffic. Some load balance modes require the switch to treat multiple physical links as a single logical channel, and the switch must be configured accordingly to avoid viewing the links as independent paths that could create loops. Other modes can work with a switch that is unaware of the bond, especially in active backup configurations where only one link is active at a time from the switch's viewpoint. Application traffic behavior matters because the performance benefit of load balancing is often realized across many flows rather than within one flow. If an application uses many parallel connections, load balancing can spread those flows across members and increase aggregate throughput. If an application uses a single large flow, it may still be limited by one member link depending on hashing and distribution logic. The exam expects you to connect mode choice to traffic patterns and to avoid assuming that pooling always doubles speed for every workload. When you match the mode to both ends and to the workload, bonding becomes predictable and useful. Misconfiguration risk is high when ends disagree on bonding expectations, because bonding is a negotiated relationship even when it is not explicitly negotiated by protocol. If the server believes two links are a single logical bond, but the switch treats them as two independent connections, traffic can be misdirected, duplicated, or dropped depending on how the bond mode behaves. If the switch expects a bundled channel, but the server is not configured to participate correctly, the switch may block ports, flap states, or forward unpredictably. In load balance modes, disagreement can cause loops because both links may forward simultaneously in a way the switching topology does not expect, especially if there is no proper aggregation configuration at the switch. In active backup modes, disagreement can cause intermittent failures because the switch may learn media access control addresses on one port and then see them move, triggering security features or causing transient forwarding issues. The exam tests this by describing unstable connectivity after bonding changes and asking what went wrong, and the correct answer often involves mismatched expectations across ends. This is why bonding must be treated as a coordinated change, not as a server-only tweak. When you respect that both sides must agree, you reduce the most dangerous bonding failure modes. A common beneficial scenario is bonding server uplinks for resilience and maintenance, where the goal is to keep the server reachable during link failure or while performing planned work. A server with two network interfaces can be connected to two switch ports, and bonding can provide a single logical interface that remains up even if one cable is unplugged or one switch port fails. This supports maintenance because you can replace a cable, move a port, or reboot a switch without taking the server offline, assuming the bond is configured correctly and the switch side is compatible. It also supports failure tolerance because a single physical link failure does not isolate the server. In environments with high uptime requirements, this is a common pattern for server access to the network. The exam often frames this as, we need redundancy for server connectivity, and bonding is a natural answer when paired with correct switch configuration and testing. The scenario also highlights why documentation matters, because knowing which physical ports correspond to the bond is critical when diagnosing issues. When you can describe the maintenance benefit clearly, you show the intended use case. A major pitfall is one-sided bonding, which can cause loops or intermittent drops because the network sees behavior it cannot interpret correctly. If a server is configured for a load balancing bond and uses both links actively while the switch ports are configured as independent access ports, the switch may forward traffic on both paths in ways that create a loop through upstream switching, especially if the ports land in the same VLAN and spanning tree assumptions are violated. Even when loops do not form, one-sided bonding can cause intermittent drops because the switch learns the server's address on one port and then sees it on another, leading to address flapping and unstable forwarding. This can manifest as short bursts of packet loss that are hard to reproduce, especially under load. The exam tests this because it is a classic configuration mismatch that produces ugly symptoms, and the fix is to align switch and server configuration so both sides agree on the bonding model. The key is that bonding changes how a host uses the network, and the network must be prepared to see that behavior. When only one side changes, the network interprets it as abnormal and reacts unpredictably. Another pitfall is assuming bonding doubles single-flow throughput always, which is a common misunderstanding that leads to disappointed performance tests. In many load balance bonding configurations, a single flow is mapped to one member link to preserve ordering, and the bond increases throughput primarily by distributing multiple flows across members. This means a single large file transfer may not exceed the speed of one link even though the bond contains multiple links, while multiple simultaneous transfers can collectively approach the combined capacity. The exam expects you to separate per flow capacity from aggregate throughput across flows, because that distinction is foundational to understanding bonding and link aggregation behavior. If your workload is dominated by one flow, bonding may provide redundancy but not the throughput improvement you expect. If your workload consists of many concurrent sessions, such as multiple clients or multiple service connections, bonding can improve aggregate capacity significantly. Misunderstanding this can lead to incorrect conclusions about whether bonding is working, when in reality, the distribution logic is working as designed. When you interpret results correctly, you can choose bonding for the right reasons and validate it with the right tests. Quick wins include testing failover and monitoring errors per member link, because bonding success is proven by behavior, not by configuration text. Failover testing means intentionally disconnecting a member link or disabling a switch port and observing whether connectivity persists and whether applications experience only minimal interruption. This validates that the bond mode behaves as intended and that the switch side configuration supports it. Monitoring errors per member link is important because one bad cable or one marginal port can degrade the whole bond's performance or cause intermittent drops even if the bond remains up. Member-level monitoring also helps detect uneven distribution, unexpected flapping, or physical layer issues that are otherwise hidden behind the logical bond interface. The exam often rewards answers that include testing and monitoring because they demonstrate operational awareness. A bond that has never been tested is a risk because the first real failure becomes the test, and that is a bad time to discover misconfiguration. When you test and monitor, you convert bonding from an assumption into a verified resilience feature. Operationally, keeping documentation aligned with actual switch ports matters because bonding failures are often diagnosed physically, and misdocumentation wastes time during outages. If the documentation says a server bond uses specific switch ports, but the cabling has been moved or ports have been repatched, troubleshooting actions can target the wrong interfaces. This can lead to accidental disruption, such as disabling the wrong port or unplugging the wrong cable, which can escalate an incident. Accurate documentation also supports change management because bond configuration changes often require coordination between server teams and network teams. Documentation should include port identifiers, VLAN membership, allowed trunk settings if relevant, and the expected bond mode so both teams know what the link should look like. The exam expects you to treat documentation as part of maintainability because maintainability affects availability. In a bonded design, the physical mapping between logical interface and physical ports is a critical piece of the puzzle. When documentation is accurate, response is faster and safer. A useful memory anchor is mode, match, test, monitor, document bonding, because it captures the life cycle of making bonded links reliable. Mode reminds you that bonding behavior depends on the chosen approach, such as active backup versus load balancing. Match reminds you that both ends must agree, meaning the switch configuration and server configuration must support the same expectations. Test reminds you to validate failover behavior and performance under controlled failure conditions rather than trusting configuration alone. Monitor reminds you to watch member link errors and distribution behavior so you can detect degradation early. Document reminds you that physical port mapping and configuration intent must be recorded to support troubleshooting and safe changes. This anchor is useful for exam reasoning because it covers the most common failure causes: wrong mode, mismatched ends, untested failover, hidden member issues, and poor documentation. When you can walk through the anchor, you can design and troubleshoot bonding with discipline. It also gives you a structure for explaining your answer clearly. To diagnose uneven throughput in a bonded link, start by asking whether the workload is single flow or multi-flow, because bonding often improves aggregate throughput more than per flow speed. If a single transfer is slow, it may be pinned to one member link by the bond's distribution logic, while other member links remain underused. Next, consider whether one member link has errors or reduced capacity, because the logical bond can mask a degraded member until you look at per port counters. Then consider whether hashing distribution is uneven, causing many heavy flows to land on one member, which can happen depending on how the bond chooses link assignment. Also consider whether the switch side and server side configurations truly match, because mismatches can cause traffic to be misforwarded or to flap, reducing effective throughput. The exam expects you to reason through these factors rather than assume the bond is broken simply because you did not see a perfect doubling. Uneven throughput is often a measurement and distribution issue, not a failure. When you can explain why it happens and what to check conceptually, you show the correct level of understanding. Bonding is different from routing redundancy, and this difference matters because it changes where failover occurs and what failure domains are covered. Bonding operates at the link level, combining multiple physical connections into one logical interface between a server and the immediate switching layer. Routing redundancy operates at the network layer, providing alternate paths between subnets or sites, often across different routers and links, and it can route around failures beyond a single host uplink. Bonding can keep a server connected if one cable fails, but it does not inherently protect against upstream routing failures, core outages, or provider failures. Routing redundancy can provide alternate network paths even when a particular link fails, but it does not prevent a single server uplink failure from isolating the server if the server has only one physical connection. The exam tests this distinction by asking which mechanism addresses which failure, and the correct reasoning is to match the redundancy method to the failure domain. Bonding is local and link-focused, while routing redundancy is broader and path-focused. When you keep the layers straight, you can choose the right tool for the requirement. To close episode 68, titled Bonding, When to Bundle Links and What Can Go Wrong, the key idea is that bonding combines links to improve redundancy and potentially throughput, but it must be treated as a coordinated design between server and switch with clear expectations. Active backup modes prioritize failover simplicity, while load balance modes can increase aggregate capacity when traffic consists of many flows, and the correct mode depends on switch support and application behavior. The most serious failures come from misconfiguration when the ends disagree, especially one-sided bonding that can cause loops or intermittent drops. Another common misunderstanding is expecting single-flow throughput to double automatically when many bonding approaches distribute by flow rather than by packet. Quick wins like failover testing and member-level monitoring validate that the bond behaves correctly and reveal degraded links before they cause outages. Documentation that maps logical bonds to physical switch ports is essential for safe troubleshooting and change control. Your rehearsal assignment is a mode selection drill where you take a server scenario, state whether you would use active backup or load balance, and explain what both ends must support and how you would test it, because that drill is how you demonstrate bonding decision patterns the way the exam expects. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.